Chapter 6 of DSP, in which we will study we'll start discussing the filters. We're going to look at the DSP systems from the perspective of filtering, as how the DSP system equations, or how the systems can be created to represent a filter. We are going to look at different filter types, or introduce different filter types, which I think most of you know. We have 4 types of filters in general: low pass, high pass, band pass, and band stop. Now when we have digital filters, the response is pretty similar to the response of analog filter, except we do have some sort of variances or pulses in the pass band and the stop band. And we are going to discuss, especially in chapter number 7, we are going to discuss why do we have those variations and how to take care of those variations. So we're just gonna, in this chapter, we're just gonna look at the 4 basic filter types towards the end of the chapter. But before that, we are going to look at the system that we have been studying so far from the perspective of a DSP filter. So let's move on and let's review the difference equation and digital filtering. So as we discussed in different chapters and in the last chapter as well, that when you have a DSP system, and in this chapter as we are discussing filter, so the system is going to represent a filter. So when you have a DSP filter, of course, as any other DSP system, that is represented by a difference equation in the time domain, in n domain. That filter can also be represented by a difference equation. And the basic idea is that you have unfiltered input coming in, then you have the digital filter through which the input is going to be passed, and based on what type of filter you are using, the output will be a filtered output. And again, if you are trying to suppress low frequencies, of course the digital filter is going to be a low pass, the high pass filter. If you're trying to suppress the high frequencies, the digital filter is going to be low pass filter. If you're trying to extract a band of frequencies, your digital filter is going to be a band pass filter. And if you're trying to stop a band of frequencies, then your digital filter is going to be a band stop or a band reject filter. So again, everything is same. The only thing that will be different is, instead of calling the DSP system as a general DSP system, we're just going to be calling it a DSP filter or a digital filter. So we discussed that any DSP system can be represented by a generic equation, which is your difference equation, which is given by right here, this. So this is, you know, y of n, a1 y of n minus 1, and all those is equal to b naught xn. So we know that y of n is the current output, y of n minus 1 is the previous output, y of n minus 2 is previous output if you go 2 time steps back, and a1, a2, an are the coefficients of, or the multiples of those y components. And likewise, your x of n is the current input, b naught is the multiple of that, or your amplification of that, and likewise x1 minus 1, xn minus 2 are the previous instances of the input, and b1, b2 are the multiples or amplification factors for that. Now of course, our goal is to determine what is the current output based on the current value of input and past value of inputs and the past value of outputs. So we have to determine y of n. So y of n, of course, is b naught xn b1 x1, and then you're gonna take this whole thing on the other side and subtract it. So in general, your difference equation can be represented by this. Now remember, y of n, the coefficient is 1, and that should always be 1. So in case if it is not 1, if it is 2, 3, 4, 1.5, whatever number, make sure you have to make it 1. So what you're going to do, if there is any coefficient associated with y of n, is to divide both sides of this difference equation by that coefficient, so that you will make this coefficient of y of n to be 1, and of course the other coefficients are going to be adjusted when you're dividing both sides by the coefficients of y of n. So remember that, don't leave it as anything except 1. Okay, and it is, I'm putting it down over here as well. Okay, let's look at example 6.1. I think someone asked me about this example as well, so let me go ahead and kind of clarify it. So we have this difference equation, y of n plus 0 minus 9 y of n minus 1 is equal to x of n plus 0.5 x of n minus 1. Now, remember from the earlier chapters we discussed the impulse response to be infinite impulse response or finite impulse response. Likewise, when the DSP system is a filter, there are two types of filters: infinite impulse response filter and finite impulse response filter. And again, what is the difference? If the filter impulse response is comprised of infinite number of terms, it is infinite impulse response or IIR filter. And if filter's response is comprised of finite number of terms, then it is a finite impulse response, or what we call FIR or FIR filter. How do you determine it? The same way that you determined earlier in chapter 2 or chapter 3, whichever chapter we discussed. That is, if in your difference equation you have any previous instance of yn minus 1, yn minus 2, that is going to produce an infinite impulse response, and your filter is going to be IIR filter. But if you don't have any previous instance of y, only x and previous instances of x, then it is a finite impulse response system in time domain, right? In the z domain, as you will see, if you have finite impulse response system, and when you take the z transform of both sides, basically your transfer function h of z will have k number of poles at z is equal to 0. K is multiplicity, basically based on what is the highest power of x over here. So for example, if you have xn minus 3, then you will have 3 poles when you take the z transform, as you will see in one of the examples, and you're going to do problems as well. So in finite impulse response, if your system is finite impulse response, from the z equation, from the h of z, you will have multiple number of poles, but only at z is equal to 0, not at any other place, any other point. So that is a finite impulse response system. But if you have infinite impulse response system, your h of z will have poles at multiple points in the z domain, right? Not necessarily all the poles will be at z is equal to 0. So that's how you're going to distinguish the finite impulse response and infinite impulse response filters from h of z. And again, we will do examples about that as well, and discuss some more in chapter number 7 and chapter number 8. So in this one, let's say this is a finite impulse response system equation, finite impulse response filter equation, or sorry, not finite impulse, infinite impulse response system equation, because you have y of n minus 1. And basically we are saying that if x of n is represented by this series 0.6 to the power n un, and the previous value of y of negative 1 is 1, then what will be y of n? That is, what will be y of 0, y of 1, y of 2, so on and so forth. So we are doing only few terms, in the first few terms. So all we have to do is use the difference equation, write it down as y of n is equal to xn plus 0.5 xn minus 1 minus 0.9 y of n minus 1, which is right over here. And then we go ahead and start plugging in the numbers. So y of 0, when n is equal to 0, that's going to be x of 0, x of negative 1 times 0.5, and y of negative 1 times 0.9. So x of 0, of course, since x of n is 0.6 n, 0.6 to the power n un, x of 0 is going to be 0.6 to the power 0 u sub 0. All right. So u sub 0, of course, is a step function. It's going to be activated as soon as n will become 0, and for all positive values of n, it is going to be 1. So basically, you are looking for this number. So 0.6 to the power 0 is 1. So that's why x of 0 is 1. 0.5 x of minus 1. Now x of minus 1 is what? Since it's a step function, and a step function only activates when the argument is 0 or positive. That means when the argument of x is negative, it is going to be 0. And that's what you see over here. 0.5 times 0, so I just put 0 over here. And y of negative 1 is given to you, which is 1. So we go ahead and put that here. Negative 0.9 times 1 is 0.9. So the y of 0 is 0.1. All right, y of 1, n is equal to 1. So you're going to go ahead and put x of 1 plus 0.5 x of 1 minus 1, which is 0, minus 0.9 y of 1 minus 1, which is 0. So x of 1 plus 0.5 x of 0 minus 0.9 y of 0. X of 1, again, you're going to go ahead and put n is equal to 1 here, so 0.6. So x of 1 is 0.6. X of 0 is 0.6 to the power 0, 1. So 0.5 times 1, 0.5. And y sub 0. So y sub 0 is this, the last value. So that was 0.1. So 0.9 times 0.1, which is 0.09. So y sub 1 is going to be 1.01. And the same way you're going to figure out the rest of the values. I just did 5 values because, of course, it is an infinite impulse response system. So number of values is going to be infinite, and of course, it's going to be infinite because the x value are also keep on going. Although it will become smaller and smaller, but still it's an infinite impulse response system. So even though the values of x will become smaller and smaller, which are the first two values, x of n plus 0.5 x of n minus 1, but the system, since it's an infinite impulse response system which depends on the last value of y, that will always be here, right? So this will be a never-ending sequence. So this is how you're going to figure out the response of the filter for any input through your difference equation. Now in the next MATLAB project that I project number 4 that you will have to do, the first part of that project is this, that is h of z is given to you. First you are going to create the difference equation from h of z, as we're gonna see pretty soon how to create it, and then from that difference equation I'm providing you the input x in a file, which is a speech file that you used I think in project number 3 as well, and that file represent x values. So you're going to use that file, and like we are doing x of 0, x of 1, so in that file that's going to be the same thing, and you are going to create the equation, and then you're going to calculate y of 0, y of 1, y of 2 as I'm explaining you over here, but of course in MATLAB, and it is very easy, it's not difficult. So that will be the first part of your project. You're gonna find the filtered output. So basically you are filtering out based on the filter that is given to you. You are filtering out the speech file, and you will see when you play the original file and the filtered file, you will see the difference in the sound when you do that. But the first part is basically to create this and figure out the output for the corresponding inputs, and basically observe the spectrum of the original input and the filtered output, and then play the sound. All right, let's look at example 6.2. Again, this is an example which is IIR filter. Why? Because of this. Again, this is an infinite impulse response filter. And you have x of n, which is discrete values that are given to us, 6 values that are given to us, and system is relaxed. That means all the initial values of y are 0 and x are 0. If system is not relaxed, some values of output will be given to you, like in the last example. And in the last example, of course, x of n was a step function. So of course there will be no initial values of x, because the step function starts at n is equal to 0. So, but if it is given to you that system is relaxed, basically the initial conditions are 0. So observe that we have a multiple of y's of n, which is 3. So the first thing we're going to do is to divide both sides by 3 to get rid of this coefficient of y, and that's what we did first, and recreated our, or rewrote our difference equation. And then once we have that, we went ahead and then we did the same thing that we did in the last problem, and calculated y's of n like this, and all these values. Now in MATLAB there's a built-in function which is called filter, and filter can basically produce output of a filter based on the coefficients of y and coefficient of x, that is a's and b's, and the input x. And this is how you use it. Y is equal to filter coefficient of x first, then coefficient of y, and then the input x. So if you look at this code, my coefficient of x are 1 and -5. I'll go back to this equation. Coefficient of x is 1 and -5. Of course this is going to be on this side, -5, and coefficient of y and coefficient of x are 2 by 3 and 1. Right, 2 by 3 and 1. And if you have h of z, it's the same thing. B will be the coefficient of z to the power -1, z to the power -2. B will be the coefficient of z's in the numerator, and a will be the coefficient of z's, the polynomial of z in the denominator, which correspond to y. And x is the input. And in this case, input of course is given to you, which is this. So when you run this, you observe that you will get the same result as you got from difference equation. Basically, it is doing the same thing. It is creating difference equation and giving you the same result. So in the project 4, in the second part of the project, I'm asking you to use filter command instead of creating the difference equation. Use the filter command and or filter function, and do the same thing. Take the speech input and then filter it using the filter function, and of course you will see that your results will be similar. So in project 4, basically there are two parts. The first part is you have to create the difference equation, and then filter the input using the difference equation to collect the output. And then in the second part, you don't have to create the difference equation, just you have to use the filter function to perform the filtration. Okay, so difference equation and the transfer function. So we know that the transfer function is the ratio between the output and the input in the z domain, right? And if x of n is impulse function, then h of z is going to be impulse response, which is the same as the transfer function, right? When x of z is 1, then x of n is an impulse function, and the transfer function is the impulse response of the system if all the initial conditions are 0. So this is important. If your initial conditions are not 0, first from the difference equation you are going to put the initial conditions and then create h of z, and it will not always be true that h of z is going to be the impulse response of the system. But in general, from this point on, we will discuss all the systems for which the initial conditions will be 0. Okay, so how do you get the transfer function? As we did in the last chapter, you take the z transform on both sides, and then take the ratio y sub z over x of z, and that's going to give you h of z, which will be a polynomial of z in the numerator divided by polynomial of z in the denominator. Now roots of the polynomial in the numerator are called what? Zeros, and roots of the polynomial in the denominator are called poles. And we're going to discuss this as how you describe the stability of a system using poles and zeros. So once again, if you have h of z, and let's say h of z is given by 4z square plus 6z plus 8 over 7z cube, or just z cube, plus 9z square plus 6z plus 9, let's say, So whatever the roots of the numerator, which will be two roots, of course, it's a square polynomial or quadratic polynomial, those are called zeros of the system. Why they're called zeros of the system? Because if you put the values, if you put those roots in here, then h of z is going to become 0, right? Because they're the roots, right? So let's say the roots are z minus 1, our factors are z minus 1 and z plus 2. Let's say these are the factors of the numerator. Assume that, right now, I mean. So the roots are what? Z is equal to 1 and z is equal to negative 2. Those are the roots. So if you go ahead and put that, any of those roots here, what you're gonna get? You're gonna get that factor to be 0, and since it is being multiplied by the other factor, the whole numerator is gonna become 0. So the roots of the numerator of h of z are called zeros of the system, and the roots of the denominator are called poles of the system. And what happens at poles, or when you go close to the poles, that is what happens when you go close to the roots of the denominator. Let's say one of the root is z minus 0.6 in the denominator, right? One of the factor is, sorry. So root is going to be z is equal to 0.6. How do you find root from a factor? You equate it with 0, and that will give you the root of the factor. So if you put z is equal to 0.6 over here, of course this will become 0, and the denominator is going to become 0, which will be no result. But if you go close, if you take a limit, and if it starts going close to the pole, basically your value will keep on increasing, because the denominator becoming smaller and smaller. Of course at pole your value is undefined, but close to the pole the value of h is going to be very large. So the roots of the denominator are called poles of the system, and as we see very soon, your stability of the transfer function, the stability of the system depends upon the location of poles in the z-plane, and we're going to study that topic very soon. So let's look at this example. We have to determine the transfer function of this, which we discussed in example 6.3. So again, first thing we did is we divided both sides by 3 so that there is coefficient of 1 with y of n, and then we took the z transform of both sides, rearrange everything, and h of z came out to be 2/3 of z plus 1 over z minus 0.5. Let's look at this example. Determine the difference equation of the filter from the transfer function. Okay, so let's see how do we do that. So the first thing you do when you have the transfer function, that is a polynomial in the power of z divided by polynomial in the power of z. The first thing that you do, if it is not already given in the negative powers of z's, so first you make all the powers negative. To do that, you will see that what is the highest power either in the denominator or numerator. So here z to the power 4 is the highest power. So you divide both the numerator and denominator by z to the power 4. So this is what I'm doing over here. I divided z to the power 4. So you are going to get 5z inverse plus 7z negative 2 plus 8z negative 3 and plus 9z to the power negative 4. And in the denominator, I'm going to get 6 plus 7z to the power negative 1, 9z to the power negative 2, 7z to the power negative 3, and 12z to the power negative 4. So now everything is in the negative power of z's. And then you're going to perform the cross multiplication. This goes here and this goes here. So you're going to write that. Oops. You're going to write that. And then we know that when you're taking the z transform, then anytime you have x of z, z to the power negative n, and if all the initial conditions are 0, then that is x of, let me do it k instead of n, that will be x of n minus k, right? So that's what we do over here. We first multiply y sub z with all of this, x of z with all of this, and then we distributed it, and then we took the inverse z transform, and we're gonna get 6y of n, 7y of n minus 1, 9y of n minus 2, 7y of n minus 3, and so on and so forth. Now, since the coefficient of y sub n is not 1, it is 6, we're gonna go ahead and divide both sides by 6 and finally write down our final difference equation with this. That will be our final difference equation. So this is how you will convert a transfer function into a difference equation. Alright, we're gonna go to the next topic in the next video.